So the last chapter, chapter 8, was about confidence intervals for population proportions. And we're going to switch gears and we're going to look at a different way that you might be able to test a claim for a population. And it's called a significance test. So today I'm just going to kind of introduce you to the idea of what that is, how to kind of set things up. So let's look at this scenario here. One of Mrs. Lewis's buddies, Mr. Simmons, claims to be an 80% free throw shooter. So he claims he can make 80% of his free throws. That is, he claims that the population would be all the free throws that he takes ever, that he makes 80%. So the parameter is 0.8. P is the true proportion of free throws he makes in the long run. Even though he's my friend, I really doubt his abilities, and here's what I suspect. I suspect that he's not as good as he says, therefore I suspect that the parameter is less than 80%. So I'm going to put the claim to the test, and I say, all right, Mr. Simmons, I want you to take 50 free throws in front of me, and he does, and he only makes 32 of the 50 right in front of me, so I witnessed that. Does this provide convincing evidence that he's less than an 80% shooter? So let's kind of pick this apart a little bit. You start by looking at, do I have any evidence at all that he might be exaggerating his abilities? So what is the little piece of evidence that we do have that he may not actually be that good? What did he do right in front of me? He only made 32 of 50, so let's write he only made 32 of 50, or if you divide that out, 32 out of 50, the proportion that he made in front of me was 0.64 of his shots. So I have a statistic. I have a sample proportion. I have p hat, and it was 0.64, which is less than the 80% that he claims. So that's my little bit of evidence. Now we know that may not be enough to prove, just one single sample may not be enough to prove. But we're going to perform a significance test. So before we do that, there are two explanations why he only made 64% of the shots. The first explanation could be that it just happened by chance, he was just having a bad day, and he really is an 80% shooter. So let's put, one of the explanations is that the 32 out of 50 happened by chance, and he really is an 80% shooter. He could have just been having a bad day. Could have happened by chance. And we're going to kind of see how likely it is that it was just by chance. The other explanation of why he did so poorly in front of me is, well, he's just less than an 80% shooter. He's exaggerating. It's got to be one of those two things. Either he just got unlucky, or he really is not that good. How can we decide which of these two explanations is more plausible? Instead of having him sit there or stand there at the free throw line and shoot baskets for 5 days, we can have the computer simulate those 50 shots that he took and see how likely it is that out of 50 shots you would only make 32 of them. So I want you to look at this dot plot here, and I want you to look at this phrase that's really important. This part that says, assuming that he really is an 80% shooter. If he truly is an 80% shooter, that's what's being simulated here. I want you to look at how many times out of 400, so this simulation, there are 400 dots here. Out of 400 sets of 50, only 3 of those times did a shooter make 64% or worse than that. 3 out of 400. Okay, so keep that in mind. So I could use a simulation to kind of see how rare that is, the likelihood of it happening by chance. Another couple of ways that we could have addressed this is using our skills that we have from Chapter 7 and Chapter 8. In Chapter 7, a long time ago, we used sampling distributions of p hat That's what's above, that's what the dot plot is, so we could run a bunch of simulations and see how likely it is. And in that chapter, we also talked about binomial distributions. To estimate. Because either he's going to make it or he's not. So it's a binomial setting, and I'm just going to put a note to myself. That was Chapter 7 stuff. We could do a probability problem. If we could prove that it had a normal shape, we could use normal CDF, kind of figure out the likelihood, or we could do a binomial distribution. The other thing that we could do, should be pretty fresh on your mind, Chapter 8, is create a confidence interval. For P, the proportion of all free throws he makes in the long run, and see if 0.8 is a plausible value. That's Chapter 8. I could create a confidence interval which would tell me, hey, I'm pretty sure the proportion of his shots that he makes in the long run is somewhere between here and here. And if 0.8 is in that interval, then it is a plausible value, and maybe he really is telling the truth. So those are two ways we could have tackled that. But we're going to, where this is leading is we're going to talk about a significance test, and that's just basically another way that we could test this claim. And when you do a significance test, it's always going to start out with some hypotheses. And there's something called a null and an alternative hypothesis. And you're going to have to write both of those in that order. You'll write your null hypothesis and your alternative hypothesis. What notation is used for each, and what are some common mistakes? All right, so let's talk about the null. The notation for null hypothesis is H with a little sub-0 or sub-O, H naught. That's the notation that's used, okay? And then you're going to put a colon and you're going to say, here's my null hypothesis. And it says right there that this is the claim that we are weighing evidence against. So because I think Mr. Simmons is exaggerating, I'm going to try to weigh evidence against his claim that he's an 80% shooter. And then you just need to define the parameter where P is the proportion of made shots in the long run. P equals proportion of made shots in the long run. Squeeze that on there. You'll always write your null hypothesis first, so you'll always do H naught first. It's always going to have an equal sign in it. It's not ever going to have a different symbol than an equal sign. So that, I think the null will be pretty easy for you to set up, because it's always going to look like that. And then just be sure, one of the common mistakes you're going to see on the next page is that people forget to define the parameters. So be sure you just do that. And then underneath that, you'll list the alternative hypothesis, and it says, well, what that essentially is the claim that we're trying to find evidence for. And here is the notation for alternative hypothesis. It's a capital H with a little subscript lowercase a, ha. That's your alternative. And I'm trying to find evidence for this. I really think that he is, less than an 80% shooter. So I think the proportion of shots that he makes is lower than that. You don't have to then redefine your parameter here. You've already done it next to your null. So you would just put these pieces together, and that's how you're going to always start a significance test. And that's kind of the main point of today, is you getting some chance to practice with writing your hypotheses. So if you will turn the page, oh, by the way, these will always be the same exact number, and I think I messed up in my Schoology notes. I think I accidentally wrote the 0.64 right here. But these, if your null has 0.8 in it, your alternative has 0.8 in it. Those numbers will always match. Some of your homework problems today are like, hey, take a look at these hypotheses and figure out what's wrong with them. If these numbers don't match, then it's incorrect. If there's not an equal sign in the null hypothesis, then it's incorrect. So those are some things that I saw in your homework. Here are some common mistakes when people write their hypotheses. They will accidentally use statistics in their hypotheses instead of parameters. You need to be using parameters, and this entire chapter is about proportions. We're not even going to look at significance tests for means, population means, until chapter 11. Okay, so be sure that in your hypotheses you're putting P, or you'll see on the next page sometimes it's different than that. But be sure that you give both hypotheses, not just one of them. Give the null, give the alternative. Make sure you define your parameter. And then don't do what I accidentally did. Let me show you. I did this, and I'll have to change it in Schoology. But don't use the statistic that's given in the problem. That's what I accidentally did here, and I should have known better. But don't use the statistic that happened. Use the data to form, don't use the data to form your hypotheses. Let the question lead you into knowing what to write. Okay, we're going to get to this a little later on in the chapter, and I'll be able to expand on it a little bit. But the difference between a one-sided and a two-sided alternative hypothesis. So this only applies to the alternative. The null, once again, is always going to have an equal sign. A one-sided alternative hypothesis uses the symbols less than or greater than. What you're saying there is, like with this Mr. Simmons thing, I either think he's less than an 80% shooter, or maybe I think he's better than 80%, then I would use greater than, if that was the claim I was trying to find evidence for. So one-sided means it's either less than or greater than that null hypothesis value. A two-sided alternative hypothesis uses the symbol not equal to. Now make a note, okay, because these are a little bit more rare, but you're going to see it. That's two-sided, because what that really means is different than, which means different than. In other words, I don't really know if it's less than or greater than, I just don't think it's exactly that. So if this applied to the Mr. Simmons free throw shooting, and I use this symbol, it would be because the question said, I just don't think he's truly an 80% shooter. I don't know if he's better or worse, I just don't think it's that 80%. And then I would use the not equals to in my alternative hypothesis, which just means I think it's something different than 80%. Lower, higher, I don't know. And then the little tip that I have for you is how you're going to know what symbol to use is really just the wording in the problem. Use the wording of the question to guide you in what symbols to use. Not the data. Again, don't use the fact that he only made 64% of his shots. Don't use that and say, well, then that's less than 80%, so I'm going to do that. It really just goes back to what claim are you trying to find evidence for? I think he's exaggerating. I think he makes less than that. That's why I use the less than symbol. And then there's this huge concept that's embedded throughout this entire chapter that's so very important for you right here. And it's something called a p-value, capital P value. You're going to see a lot of questions on quizzes and tests about interpreting what a p-value is. And you're eventually going to learn how to calculate that, but today in the word problems you'll just be given a p-value. But I want you to start kind of knowing what that tells us. A p-value is this, and I would highlight this, and I would, if you're a flashcard person, I would make a flashcard on p-value, okay? What it is it's the probability of giving evidence for your alternative hypothesis as strong or stronger than the observed evidence. So the p-value in this shoot free throw problem is going to be the probability of getting evidence as strong or stronger than the less than 64% that happened in front of me. And so it says that a little bit more gracefully than how I just said it in the second bullet point. Assuming that Mr. Simmons is an 80% free throw shooter, there is a blank. Okay, so what you're going to put in the blank is what we use from the simulation, because that's really all we have to go by today. You'll learn how to calculate that later. But 3 out of 400 and that is from the dot plot. Probability of getting a sample proportion as small or smaller than 32 out of 50 by chance alone. So let me illustrate what a p-value really is. Draw this picture. Because you know in statistics, everything goes back to this normal curve. Your null hypothesis would be in the middle there. That's the center. Your evidence, in this case our evidence was lower than the null, it was only 64%. Your evidence is going to be your threshold. You just want to write evidence right there. And then the p-value is the probability that you get something as extreme or more extreme, so maybe even less than 64%. That right there is, that region is exactly what a p-value will tell you. It's the probability that you get something as strong or stronger than the observed evidence. Okay, so what is the p-value? Why is it so important? What does it tell us? Well, if the probability is really small, then we can rule out random chance, and that means that we have convincing evidence for alternative. So I want you to write, therefore we reject, this is how we say it, we reject the null hypothesis. If the p-value is small, we reject the null, and we do have convincing evidence for the alternative. If the probability isn't really small, and we know that pretty much our threshold in statistics is 5%, okay? If it's not, then we can't rule out chance, so then we wouldn't have convincing evidence for our alternative. So listen to how weird this is. Instead of saying we would accept the null, we say fail to reject the null. And I'll explain on the next page why we can't just say, like, why does it have to be that awkward wording? Reject or fail to reject. That's the verbiage you must use. And I'll give you a little bit more insight here in a second when we turn the page. Okay, well I just said if the p-value is small, well, how small? So this bullet point is really important. The significance level, which is denoted by a little alpha, that's going to determine if a p-value is small. In most statistics problems, if you're not told what the significance level is, then use 0.05. And we've talked about that since the beginning of the year. It's no coincidence that that's pretty much our 5% threshold. And again, that's called the significance level. Alpha. It may tell you in your word problem to use alpha of 0.01 or alpha of 0.10. Those are other common ones. But you're basically going to compare your p-value to alpha. So look at that last bullet point. If the p-value is smaller than alpha, the significance level, then we have convincing evidence for the alternative hypothesis. Just make a note to yourself. Sometimes alpha might be 0.01 or 0.10. That would be the small and large end of alpha. If you're not told what significance level to use 0.05. Use that 5% to determine if it's statistically significant. And if you're thinking, well, what are these other ones? We'll talk about that in the next set of notes, like why you might, if you get to choose a significance level, you might want to choose a smaller one or a larger one, and we'll talk about that next time. All right, this is hugely important in teaching you the phrasing for not just the AP stats exam, but statistics in general with these hypotheses tests. You either need to say, because the p-value of blank is less than alpha, we reject the null, there is convincing evidence for, and then just put your alternative hypothesis in context. So you're either going to say that at the very, very end, or you're going to say because the p-value is, and you can say greater than if you want, instead of not less than, you can say greater than. If the p-value is greater than the significance level, we do not reject, or we fail to reject, the null. So there's not convincing evidence for the alternative in context. And we're going to practice that right now. I want you to go back up to this little blank space that we have for the free throw problem. And we found out that the p-value is 3 out of 400, just based on that simulation on the dot plot. And that is 0.0075. It never told us what significance level to use in this problem, so let's use 0.05. And so now we're going to get to make our conclusion about our claims. And I want you to put, since the p-value of 0.0075 is less than significance level of 0.05, and then I'm just following what it says at the bottom of the page, we reject and you don't have to put that one in context because the guts of it is this very last sentence. We have convincing evidence, or you could put there is convincing evidence that, let's put it in context, Mr. Simmons is exaggerating I'm not the best speller. Are there two G's in exaggerate? Some of you are saying yes, some of you are saying no. Okay, don't judge me. Don't judge me, I don't know. That looks funny, I think there's two G's. I think that Mr. Simmons is exaggerating, and he is less than an 80% shooter. So eventually, you're just going to be given a paragraph of information. You're going to have to write your hypotheses. You're going to have to perform this whole calculations part. Remember that state, plan, do, conclude stuff? That's going to be applicable here as well. We'll eventually look at that 4-step process. But at the very end, you're going to go back and you're going to compare your p-value to the significance level, and you're going to be able to write the sentences. All right, turn the page. that's where that could have gone, whatever. Let's look right here where it says, what are some common errors that students make in their conclusions? Please, please, please know that you have to compare the p-value to the significance level. Like, you have to put that in your phrasing. You can't just jump right to, we reject the null. You have to tell why. Be sure you put it in context. Don't just use HO and HA. Be sure that you put at least the HA in context. Okay, here's why we don't accept the null. That's a very common mistake that people make. They say, oh, well, then we accept the null. Well, failing to reject it doesn't mean that it's necessarily spot on, because remember, the symbol that we use is equals to. So it's not necessarily true that it's exactly that value. And think about confidence intervals, okay? Confidence intervals give you a little bit of play. We're pretty sure it's between here and here, so we can't really say it's exact, even if we fail to reject it. So just know that that's the why behind why we can't just say accept. So let's look at this last problem, and we'll just kind of work through step by step and see if we can put all the pieces together. Mike is an avid golfer who would like to improve his play. A friend suggests that he should get new clubs, and Mike try out his 7-iron. Based on years of experience, Mike has established over time that the mean distance he can hit a golf ball is 175 yards on average, with a standard deviation of 15 yards. Now, here's what he's hoping. He's hoping that if he goes ahead and purchases the 7-iron, that it will make his shots more consistent or less variable. So we're talking about the standard deviation. He's wanting to lower his standard deviation. So he goes to the range and he hits 50 shots, and this is his sample standard deviation. So there's maybe some evidence that we have right there that it did improve his shot. It made it more consistent, it lowered the variability, because now the standard deviation is lower than 15. So it says right here, go ahead and define your parameter of interest, state your hypotheses, and go ahead and tell me what evidence we do have for the null. And so, really, I think that should be, for the alternative. That's a little tiny A there. I always like to just write the hypotheses first, and that's what you'll see most people do. So you're always going to start with your null. You know there's an equal sign in it. And while this entire chapter is about population proportions, this one kind of dumb little problem is about standard deviation. It's kind of a one-off. Now he's hoping that, what symbol should I use? Greater than or less than or different than? He's hoping to make his shots more consistent or less variable. So does he want that? Does he want his new 7-iron to provide this less than this value, greater than this value, or just anything other than this value? Less than, yeah. Wants his shots to be more precise. Remember, precision and spread go together? Okay, we just need to make sure we define our parameter and then kind of just tell what our evidence is. Let's go ahead and put where sigma is the true standard deviation of all shots in yards in the long run. Now the sum evidence that we have, I'm just going to go up here and write it, is that the new standard, the statistic, the new standard deviation that he got is 13.9 yards. That's some evidence in favor of that alternative hypothesis, because it is less than 15. So that was our task on part A, and that's really what you're going to practice a lot in your homework today, is getting really comfortable popping out those hypotheses and defining that parameter, okay? A significance test using the sample data produced a p-value of 0.28. Remember, eventually you'll be able to calculate that. Today it's going to be given to you. Sketch a picture of what is being calculated and interpret the p-value in context. Okay, again, I can't stress this enough. The interpreting the p-value, that's kind of what tends to be difficult for people, is putting into words what that value really means. So here's what's going on. I'm going to have you sketch this picture. Remember, your null value goes in the middle. Your evidence, which was that 13.9 yards, which is on this side of 15, place that. That's going to be the threshold. And we're trying to find evidence as extreme or more extreme than this. And that's why I'm going to shade to the left. So that p-value, that's what that point, that's where the 0.28 would be, is it's the shaded region. And let's put into words what that actually means in context here. Here is how you would write this, okay? Assuming, you're always going to assume that the null is true. So look what we wrote up here in the null. Assuming that the new 7-iron does not make his shots more consistent. Assuming that the new 7-iron does not make his shots more consistent. There is about a 0.28 probability of getting a sample standard deviation as low or lower than 13.29 yards. So take a second and kind of stare at that. When you are interpreting p-values, you're going to assume that the null is true, because what you're saying is, what's the probability that the alternative hypothesis, the evidence that we have, what's the probability that that happened in by chance? And then the putting it all together part is, they didn't tell us what significance level to use. So let's put, we will use a significance level of, essentially that's your 5% threshold for statistically significant. Alpha equals 0.05. Okay, here's that sentence frame that you need to get used to. Since the p-value of 0.28, you can put is greater than, or you could put is not less than, but regardless, the p-value here is greater than the significance level. And when that happens, we fail to reject the null. You don't have to put that part in context. It's the next sentence that will have context to it. There is not convincing evidence. Because think of it this way, if you fail to reject the null, that's kind of like if your brain wants to tell you you're accepting the null. Okay, fine. Well, you've got to either accept one or the other, right? Or fail to reject one or the other. So we're failing to reject the null, therefore we don't have evidence of the alternative. There is not convincing evidence of HA, comma, that the new 7-iron makes his shots more consistent. If you wanted to throw in there, you know, the new 7-iron doesn't lower his standard deviation, that's also fine. But this would be plenty, just putting it in context there. So all of these components are necessary. Compare the p-value to the significance level. Say whether you reject or fail to reject the null, and then the last sentence is either there is or is not convincing evidence of HA in context. That's it. And that's all you're going to practice today, and then I'll kind of lead you into doing more of the calculation stuff next time.